When we read, the experience feels continuous. Words trigger imagery, emotions, and memories in a seamless flow. But beneath that subjective experience, the brain is executing a highly mechanical data extraction process. Comprehending written information is not a single act of absorption. It is a strictly sequential, two-tiered cognitive pipeline. In the first tier, the brain parses the raw linguistic code to build a rigid, hierarchical semantic network. It captures exactly what the text says, word for word. But to actually understand the material, the brain must execute the second tier. It abandons the linguistic code entirely and constructs a non-linguistic, multidimensional mental simulation of the described reality. Cognitive psychologists distinguish these two distinct structures as the text base and the situation model. Tracking this exact sequence explains why human memory retains certain details, instantly discards others, and stubbornly resists revising errors. To see how a sentence becomes a structural memory trace, we must look at how the brain handles raw syntax under the strict constraints of working memory. This chart breaks down a sample sentence about cardiac anatomy using a method developed by Walter Kinch, known as propositional parsing. The parsing mechanism divides the sentence into base semantic units called propositions. Each proposition consists of a single predicate, like first, possess, or for, attached to specific arguments, like chamber or heart. By identifying shared arguments, the brain links these units together. One proposition serves as an argument for the next, stacking them into a raw hierarchical network called a microstructure. But the short-term memory buffer, a variable researchers call parameter I, has a severe bottleneck. It can only hold 1 or 2 sentences worth of propositions during a single processing cycle. As new text arrives, older data is forced out. To maintain coherence across these cycles, the brain employs a leading-edge strategy. It actively holds on to the highest hierarchical propositions, using them as structural anchors to connect one memory cycle to the next. Finally, the brain applies rules of selection, generalization, and construction to compress the dense microstructure into a final, manageable summary. The resulting structure is the completed text base. It maps the literal meaning of the words perfectly, but it remains cognitively shallow. It contains no physics, no spatial awareness, and no real-world logic. Deep comprehension requires a second step. The reader must pull knowledge from long-term memory to integrate with the text base, transforming the linguistic data into a running situation model. This mental simulation is structured according to the event indexing model. Instead of syntax, the brain connects events along 5 distinct dimensions: time, space, causality, protagonist, and motivation. Because processing power is limited, the brain faces a dilemma. As the narrative progresses, which specific objects does it keep active or foregrounded in working memory? Look at this experiment by Arthur Glenberg, testing how spatial association dictates memory retention. 2 textual conditions are placed alongside a blank reaction time graph. John put on his sweatshirt, creating spatial association, and John took off his sweatshirt, creating spatial disassociation. The researchers tracked how fast readers could recognize the word sweatshirt after 0, 1, or 2 distracting filler sentences that did not mention the object. In the spatial association condition, the reaction time curve remains relatively flat. The memory of the sweatshirt stays highly accessible even as new sentences are read. But in the disassociation condition, reaction times spike immediately after a single filler sentence. The readers struggled to recall the object. Because the text stated the sweatshirt was removed, the brain dynamically pruned it from the mental simulation to conserve active processing power. Memory foregrounding is not determined by how recently a word appeared on the page. It is dictated entirely by its physical relevance inside the reader's active mental simulation. Once that multidimensional simulation is running, it develops a structural rigidity. It actively resists the integration of new, contradictory facts. This creates what researchers call the updating problem, demonstrated clearly in a 1996 reading comprehension study by Harry van Oostendorp. Subjects were given texts detailing the military operation Restore Hope in Somalia. The first text explicitly placed the operation under United States command, establishing the initial state of the reader's situation model. Shortly after, subjects received a second text explicitly correcting the chain of command, stating the operation was under the authority of the United Nations. Researchers then administered an inference verification task to test whether the subjects had successfully updated their internal models with the new facts. The results showed a 30% error rate, specifically concentrated on central events. Readers repeatedly defaulted back to the initial US command scenario. The initial reading pass generates a feeling of already knowing the material. This creates cognitive friction, causing readers to process correcting UN data superficially. Encountering a contradictory fact is rarely enough to overwrite a constructed mental simulation. The brain actively defends its initial architecture. The reason for this defensive rigidity lies in the mechanical requirements of updating a network. Cognitive psychologists distinguish between surface updating and deeper updating using experimental scenarios, like a story about a storehouse fire. This network represents the initial situation model. When told a fire started near inflammable materials, the reader establishes a central node and immediately generates causal inferences, like rapid fire spread or toxic smoke. Later, a correcting data packet arrives. The adjacent room was actually empty. In surface updating, the brain acknowledges the new fact and deletes the central premise of inflammable materials, but it leaves all those downstream causal inferences floating intact within the simulation. The reader registers the correction on a superficial level, but fails to track down and eliminate the assumptions already generated from faulty data. To perform deeper updating, the reader must collapse and entirely rewire the causal network, generating new inferences to fit the empty room. Recalculating an entire inference chain demands immense cognitive energy. To justify that expenditure, the brain requires high source credibility or a compelling alternative explanation before it will commit to the change. True text comprehension is not the passive decoding of a text base. It is the active, resource-intensive engineering and the stubborn defense of a multidimensional reality.